Welcome back, everyone. This is Remote Learning Week 3. You've made it. Congratulations. Very proud of you guys. You guys are doing really awesome work. For today's lesson, we are learning about spontaneous versus non-spontaneous reactions. And this week is going to be a little bit different. You will have part 1, which will be your lesson. Part 2, which will actually be a Kahoot game. And then you have part 3, which is an assessment. And that'll be it for this week. So we'll get started with a mindful minute. Find yourself with a mindful body, sitting with your head, neck, and spine aligned. We're going to take deep breaths together. I invite you to close your eyes or look down, or you can watch the animation that's on the screen. So getting ready, we'll inhale through our nose, nice deep breath in, and exhale, releasing the air. Inhale, nice deep breath, and exhale, letting it out. Inhale, taking that fresh, energizing oxygen. And exhale, letting it go, breathing out carbon dioxide. Inhale, exhale, pushing out carbon dioxide. We're halfway there. Inhale, and exhale. Inhale, and exhale. One more. Inhale, nice deep breath. And exhale, let it go. And allow your breathing to return to normal. Check in with yourself. Ask yourself how you feel. And when you're ready, you can slowly open your eyes. Okay, so today's learning target is I can distinguish between spontaneous and non-spontaneous reactions. So we're still on the topic of redox, which is oxidation and reduction. And we're just going to distinguish between these two types of reactions. So pause the video now so you can write this down. For the do now, I want to go over this one question, which was part of your assignment from last week. This question a lot of people got wrong, so I do want to make sure we review. So the diagram and balanced ionic equation below represent two half cells connected to produce an operating voltaic cell in a laboratory investigation. The half cells are connected by a salt bridge. Determine the oxidation number of nitrogen in the negative ion in the aqueous solutions. Okay, so it's asking us for the oxidation number or oxidation state of nitrogen in the negative ion in the aqueous solutions. So you have to look at your two solutions here. We're not looking at our equation because there's no nitrogen in the equation. So we're looking at these two aqueous solutions. If you look at table E on your reference table, you'll see that we're looking at an, where's table E? Here we go. We're looking at a polyatomic ion, right? So we are looking at NO3, NO3 2. So we're looking at nitrate. So NO3 with a -1. And this 2 on the outside of the parentheses means that there's 2 of them. But we just want to know, what is the oxidation state of this nitrogen when it's in this negative ion? So we follow our rules. We know that oxygen is always a -2 There's 3 of them, so that gives us a -6. And together, this must equal a -1. So what plus -6 gives us a -1? We have +5. So your oxidation number for nitrogen is 5 plus 5, and for oxygen it's -2 in the negative ion. Okay, if you're still stuck on this before you do the assessment today, I strongly recommend going back to that lesson and watching the supplemental optional video that I posted about finding oxidation states. I think it was Khan Academy. So definitely do that before you take the assessment today. All right, so we're going to look at a new part of our reference table today, which is table J. So take out your reference table or click the link that I provided in Google Classroom, and we'll look at table J, which is called the activity series. If we look at the activity series, what are some things that you notice right away? Gives us a list of metals and nonmetals. And it looks like they're put in order from most active to least active. Okay? If we're talking about oxidation and reduction, what do you think activity is referring to? Activity is actually referring to how quickly these metals or nonmetals will lose electrons or be oxidized. So things at the top where it says most active will be easily oxidized. So anything that's higher on the chart will be easily oxidized. So it'll easily give away electrons. So the way we use this chart is, okay, just recalling, oxidation happens at the anode, reduction happens at the cathode. So the way we use this table is we can use it to identify the anode and the cathode. So the more active species, which is higher on the chart, is oxidized. It's very active in giving away its electrons. And that would be which? That would be the anode. The less active species, which is lower on the chart, is reduced and will be the cathode. So we can use this to identify what's our anode and our cathode in a chemical reaction. So let's look. Let's say we have a reaction between calcium and nickel. Anything that's higher on the chart is what's being oxidized. So your calcium is being oxidized and nickel is being reduced. So one way that I find helpful to think of this is like anything that's on top of another element will be losing its electrons, and imagine the electrons falling down the chart and going to the element that's being reduced. So calcium's giving away its electrons, they're falling down the chart, and then nickel is catching them and it's being reduced. So now that we know that, we can identify what is our anode and what is our cathode. So in this specific example, calcium would be our anode and nickel would be the cathode. And I'm just abbreviating these. Okay, so right now, why don't you look at your chart in your reference table and pick 2 elements that would be oxidized and reduced together, and then which would be the anode and the cathode. And don't use calcium and nickel because I just did that one. So from the 2 elements that you chose, whatever was on top of the chart near the top is the oxidizing agent and the anode, and whatever was underneath is the reducing agent and the cathode. So these are called spontaneous reactions. Any element that is on this chart Any two elements that are on this chart will be considered to spontaneously occur. So calcium and nickel would spontaneously oxidize and reduce. Remember that there always has to be one element being oxidized and one being reduced. If I looked at it in the other way, calcium and nickel, let's say I tried to have nickel lose electrons and give electrons to calcium, that would not be spontaneous because that would actually require a lot of energy to happen. Imagine it's like going against the grain. So nickel will not spontaneously give electrons to calcium. That would be a non-spontaneous reaction. But when calcium is giving electrons to nickel, that is spontaneous. So anything going down the chart will be a spontaneous reaction. If you're trying to have it go the other way, that's called non-spontaneous. Okay, based on table J, which metal is more active than tin but less active than zinc? So you just got to look at the chart. We'll identify tin and zinc. The abbreviation for tin is actually SN. So here's tin. And for zinc, it's ZN. So looking for zinc, here it is. Which metal is more active than tin and less active than zinc? So we're finding a metal that's between these two elements. And it's chromium, Cr. Now, the question that I want to ask you guys is, if zinc is giving electrons to tin, so going this way, is that a spontaneous reaction or non-spontaneous? That would be whoa. That would be a spontaneous reaction. I'm just going to abbreviate because it's very hard to write with this non-pen, this imaginary pen. Okay, if we're trying to give tin's electrons to zinc, is that spontaneous or non-spontaneous? That would be non-spontaneous. That would require energy for that to happen. Okay, now we're going to do a check for understanding. We're going to do the first one together, and then the rest of them are on your Google form. So using table J, identify the anode and cathode for the 5 following reactions. So for the first one, we're looking at copper ion and a iron solid atom. So using the chart, which of these would be my anode and cathode? Let me see. So copper is here, and iron is here. So iron is on top. That means what? It's more active. That means it's going to lose its electrons and give its electrons to copper spontaneously. Copper's on the bottom. It's going to be receiving electrons. So this iron is losing electrons. So that means it's being oxidized, right? Oxidation is losing. And copper is gaining electrons, which means it's being reduced. Reduction is gaining. Now, which is my anode and which is my cathode? If I remember anox, I know that anodes are oxidized. So iron must be my anode. And then red cat, copper, is being reduced. So this is my cathode. All right. So would this be a spontaneous or non-spontaneous reaction? This would be spontaneous. So for questions 2, 3, 4, and 5, this is on your Google form. You're going to answer both what is the anode and the cathode. It's a short response or open response question. So you can pause the video now and do that, or you can do that at the end. Okay, so we looked at two types of cells so far. One type of cell so far, your voltaic/galvanic cell, which is on the left. And now we're going to look at an electrolytic cell. What do you notice is different or the same between these two cells? Pause the video now and answer this to yourself. All right, so what's similar is that they are both in some sort of aqueous solution. We can see the liquid here and over here. There are two electrodes in both. We have anodes and cathodes in both. And there's a wire in both. Okay. What's different is this one has a voltmeter, which measures voltage, and this one has a battery. So this one actually has like an electrical source connected to it. And this one has some sort of like gas bubble, gas coming out of it, something like that. Okay, the main difference that we want to note is that this cell on the right has an electricity source, an external electricity source, and this is called an electrolytic cell. So remember when we talked about table J, and we said that if we're trying to do a non-spontaneous reaction going this way, that would require energy. Well, this is the energy that is used for non-spontaneous reactions. So where do we see non-spontaneous reactions? We're going to watch a quick video that shows what they look like.
Is prepped and ready, so now let's attach a piece of copper to our positive lead and then the coin to our negative lead. Now once we plug in the cord, we should be able to dip the coin down into the liquid and a copper plating should start to appear pretty quickly. Just as a first test, I'm going to dip the quarter down in and then pull it out after only about 2 seconds. Let's see if it does anything. 1, 2. You can see it's already started to get a little bit of a tint around the edges. So that's going pretty fast. Let's put it back in, but leave it for a little bit longer. 1, 2, 3, 9, 10. Boom, look at that. That is a quarter coated in copper. Now, one thing is often right where the lead is biting into it, there will be a little spot where the plating isn't very even. So I'm going to move the lead to the other side of the quarter and we'll dip it back in. This time I think we'll try leaving it in for 20 or 30 seconds. I'm going to turn it around as well so the other side of the coin is facing the copper pipe some of the time. Here we go. Look at that. That is a coin with quite a bit of copper plating it. We have a nice shiny copper colored quarter. Let's rinse off the quarter and see if we can buff that so it's a little bit shinier. We've got our steel wool. Let's lightly buff our copper and see if it brings out any shine.
Okay, so what this guy was doing here is called electroplating. So non-spontaneous reactions and this cell over here can be used for a process called electroplating. Where do we see electroplating? Well, it can be used for aesthetics or for protection. So if you know anyone that has jewelry that says gold plated or silver plated, they actually are not full gold. There's just a thin layer of gold on the top or silver or whatever it is. And for rims on cars, they usually coat these in chrome so that it protects them from getting damaged in the weather and from rusting over time. Other fun fact is the first man on the moon had a gold-plated visor to protect him from the rays of the sun. So it's super, super useful, and it's all thanks to chemistry. So we're gonna watch this quick video. I'm gonna narrate just to show you, like, very simply, how does electroplating work. Okay, in electroplating, let's say we want to coat something in copper. So we are going to use a copper electrode and something called an electrolyte. So a liquid that has copper ions in it, and this liquid will help us to plate whatever we're trying to plate. And it's called an electrolyte because it can carry an electric charge. So if we're coating with copper, we need a copper electrolyte and a copper electrode. And these two things are going to work together to coat whatever we are plating. So here's our electrochemical cell. We have the battery hooked up, and we have two anodes, two electrodes. So your copper anode is going to, over time, donate its solid copper to this brass cathode, which will over time get coated in copper. And the copper-based solution will be helpful in that process. So in the copper-based solution, which is copper sulfate, you'll have copper ions floating around and sulfate ions floating around. Now, where would the copper ions float to? Would they float to the negative end or the positive end? And where would these sulfate ions float to? The positive end or the negative end? Let's see. So opposites attract. So your copper ions in the solution will go over to the brass cathode, and it'll start to plate the brass. And electrons are flowing over here from the battery, attaching to the positive ions, which help them solidify. And your sulfate ions would move to the positive side, and they are going to neutralize each other. So the copper anode over time is experiencing oxidation, and it's going to lose the copper ions. They're going to go into the solution, they're going to travel over to the brass, and over time this process repeats itself. So the copper will lose mass over time, and the brass gets coated in a thin layer of copper. Here the video shows it's losing mass over time. Okay, so this is very similar to the voltaic cell that we saw before. Main difference is that an electrolyte is used and a battery or external electricity source is used. That part is very important. All right, so here's a definition. An electrolytic cell is an electrochemical cell that uses electricity to force electrons to travel from the anode to the cathode. This process is called electrolysis, and it's a non-spontaneous redox reaction. Pause the video now so you can write down this definition. Okay, check for understanding. The type of reaction in a voltaic cell is best described as, so we just compared two types of cells, voltaic to electrolytic. So in a voltaic cell, what happens? Voltaic cells are spontaneous, and they are both oxidation and reduction. An electrolytic cell is non-spontaneous. Okay, next one. Consider the following equation. 2H2O plus electricity gives us 2H and O2. What's different about this equation? Well, there's electricity being involved. And in which type of cell would this reaction most likely occur? We know that for electricity, it's going to happen in an electrolytic cell. So we can cross out 1 and we can cross out 3. And an electrolytic cell is going to absorb energy. So it's going to use the energy from the battery. And we know that it's being absorbed from the reaction because it's on the left side of the equation. Anything on the left side is being absorbed or taken in. All right, so that's it for today. Again, your next thing you're going to do is go over to your Kahoot review. Make sure you have your notes out, a calculator out, anything to help you, and then you will take your Google quiz assessment. Also, make sure you have your reference table out for that. All right, that's it for this week. Keep it up. Enjoy your weekend if you're celebrating the holidays. And anything you guys need, I'm here for you. Reach out via email. And my office hours are Monday from 1 to 3. Talk to you guys soon.